In this chapter, the topic of chemical reactions will be discussed. In a chemical reaction, bonds between atoms in the reactants are broken, and atoms rearrange and form new bonds to make the products. We use a chemical equation to describe a chemical reaction, with reactants written on the left and products on the right. A chemical equation is a representation of a chemical reaction using chemical formulas and symbols. If a chemical equation does not show relative amounts of reactants and products, it is called a skeleton equation. Note that skeleton equations are unbalanced. A catalyst is a substance that speeds up a reaction without being consumed, so a catalyst is neither a reactant or a product. Example of a reaction with a catalyst: an aqueous solution of hydrogen peroxide decomposes to produce water and oxygen. This reaction is very slow, but can be sped up using a catalyst, like manganese oxide. This table shows some symbols used in chemical equations. As we have seen before, the plus sign separates two reactants or products, and an arrow separates reactants from products. Q designates an aqueous solution. A formula written above or below the arrow indicates its use as a catalyst. To describe a chemical reaction correctly, the chemical equation should be balanced, which means that each side of the equation has the same number of atoms of each element. When hydrogen gas and oxygen gas are mixed, a spark will initiate a rapid reaction to form water. The first step is to write the skeleton equation. The second step is to balance the equation. Oxygen is not balanced, so we need to put a coefficient 2 in front of water. But now we notice that hydrogen is not balanced anymore. So, we have to put a coefficient 2 in front of hydrogen gas. Now the chemical equation is balanced. By classifying chemical reactions, you can more easily predict what products are likely to form. The 5 general types of reactions include combination, decomposition, single displacement, double displacement, combustion.
At first glance, these chemical reactions might seem like a mess of information, but there are patterns among them. It's helpful for chemists to sort all the chemical reactions into categories so that they can make predictions about how chemicals might react. There are 5 main types of chemical reactions: combination, which is also known as synthesis; single replacement, or single displacement; double replacement, or double displacement; decomposition; and combustion. Now, not every reaction falls perfectly into one category. Sometimes a reaction falls under 2 categories, but there are some very key features of each of these categories. Let's start with combination reactions. Combination reactions combine 2 or more substances to form a new single substance. This example is elemental magnesium and oxygen combining to form magnesium oxide. The 2 elements combined and formed one ionic compound. Even though it made 2 units of magnesium oxide, they're the same substance. So here we have the balanced chemical equation, a particulate drawing of that same reaction, and now here's a general equation for combination reactions. A plus B yields substance AB. The reverse version of this kind of reaction is called decomposition. In this reaction, things fall apart instead of coming together. A single substance breaks down into 2 or more simpler products. Here's an example of hydrogen peroxide breaking down into water and oxygen. Usually, decomposition reactions need heat or fire or electricity to get started. This reaction can happen quickly with a catalyst like yeast or manganese dioxide. So we have the equation, a drawing, and now a simple formula for decomposition. AB yields A plus B. The resulting compounds are smaller and simpler than the starting compound. Let's look at the next type of reaction. Single replacement. In this reaction, one element replaces a second element in a compound. We'll use the example of zinc reacting with iron chloride to make zinc chloride and elemental iron. The 2 metals in this case have swapped places. So here we have an equation, a drawing, and now a simple formula for single replacement reactions. A plus BC yields AC plus B. But not all single replacement scenarios actually work. In order to see if the swap will occur, we need to reference a chart. the activity series of metals. The more active metals are toward the top, and metals decrease in their activity as you move to the bottom. In the previous reaction, zinc was the individual element, and it was higher than iron on the activity series. So this reaction occurred. But if we tried to react elemental iron with zinc chloride, nothing would happen, because iron has a lower activity than zinc. Now let's look at the next type of reaction. Double replacement. This reaction is similar to single replacement, except we're starting with two compounds. The reaction has an exchange of positive ions between two compounds. In this example, copper 2 chloride and hydrosulfuric acid will swap their positive ions to make copper sulfide and hydrochloric acid. So here we have an equation, a drawing, and now a simple formula for single replacement reactions. AB plus CD yields AD plus CB. You can see from this equation that A and C have just switched places, and those represent the positive ions. Usually, a double replacement reaction creates one of three products: a precipitate, a molecular substance, or a gas. In this double replacement reaction, we started with two aqueous solutions and end with aqueous hydrochloric acid, but solid copper sulfate. This will sink or precipitate to the bottom of the container. Another possible product would be a molecule. In this example, we start with aqueous substances, but one of the products is a liquid, the water, and the other product is still aqueous. Lastly, another possible product from a double replacement reaction is a gas. Again, we start with an aqueous substance, sodium cyanide, sulfuric acid, but form a gas as a product, poisonous hydrogen cyanide gas. Don't try this one at home, folks. The last type of chemical reaction is a fun one, combustion. In combustion, an element or compound, typically a hydrocarbon, reacts with oxygen, often producing heat or light. So here's the combustion of a hydrocarbon called methane. The combustion with a hydrocarbon will always make water and carbon dioxide as products. This makes predicting the products really easy in this case. So here we have an equation, a drawing, and now a formula for the combustion of a hydrocarbon. Don't be intimidated. The x and y variables here provide a shortcut for balancing the equation as well. But not all combination reactions happen with hydrocarbons. The combustion of magnesium in oxygen is both a combustion reaction and a combination reaction. Remember, there are some reactions that can fit into more than one type of reaction.
Here we have a ribbon of magnesium. Magnesium is a metal, has the properties of luster. You can see it's shiny, it's malleable, it's bendable, can conduct heat and electricity. So what we're going to do is we're going to try to react this magnesium with the oxygen in the air. We need a little activation energy to get the magnesium to react with the oxygen, and there it is. So oxygen's reacting with the magnesium ribbon, and it's releasing a lot of light and heat energy. This is one of the brightest lights that is produced by a chemical reaction. They often use magnesium in fireworks for these bright bursts of white light. And also is extremely hot. You can get very, very, very high temperatures from this chemical reaction. Now, coming off the light, you can see a white ribbon, and that is the magnesium oxide that's being produced. So magnesium atoms are being bonded to the oxygen atoms in the air to form in that magnesium oxide product.
Many important reactions take place in water. Sometimes, a molecular equation does not give you the complete picture of what's happening in an aqueous solution. It can be useful to write out the dissociated ions in the format of a complete ionic equation. A complete ionic equation is a chemical equation that shows the dissolved ionic compounds as dissociated free ions. To obtain the net ionic equation, the spectator ions that appear on both sides of an equation, but not directly involved in the reaction, should be removed. Spectator ions are ions that appear on both sides of an equation, but are not directly involved in the reaction.
We can use molecular equations to describe substances that transform in solution, and it will be useful to use subscripts after each compound to show its phase. There's solid, liquid, and gas, and we use the word aqueous to describe ions that dissociate in solution. This is important because sometimes ions come together to form a new compound which may be insoluble in that solvent. In such a case, we will denote that it is in the solid phase, as it will crash out of solution as a precipitate. We can write molecular equations to describe solution chemistry, but we can also use net ionic equations. This summarizes the key transformation by eliminating spectator ions, the ones that just sit in solution and don't do chemistry. To do this, we start by writing the complete ionic equation. This involves splitting the ionic compounds into their respective ions. Just remember the common charges of the ions to include the correct formal charges. Subscripts in the molecular equation become coefficients in the complete ionic equation since all the components are dissociating. Anything that's present on both sides we can cancel out, like an algebra problem. These are the substances that don't do any chemistry. What's left are the two ions that come together to form a solid precipitate, which is a chemical change. This is the net ionic equation.
Mixing solutions of two ionic compounds sometimes results in the formation of an insoluble salt, called the precipitate. This depends on the solubility of the new compounds that form. In the table below, the solubility rules for ionic compounds in water are shown. For example, salts of alkali metals and ammonia are soluble in water, with the exception of some lithium compounds. Note that the alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Let's do an example. When aqueous solutions of sodium carbonate and barium nitrate are mixed, will a precipitate form? Examine the reactant ions. The cations could change partners, and the two new compounds that would form are sodium nitrate and barium carbonate. Use the table for the solubility rules for ionic compounds. Since sodium is an alkali metal, sodium nitrate is soluble in water, so that will not be the precipitate. From the table we notice that carbonates are insoluble, so barium carbonate will precipitate. Knowing this, we can write the net ionic equation.